Okay, can you see my screen?
Yes. Yeah.
Okay.
We're able to see.
Okay. Hello, everyone. Nice to meet you online. Today, I will present the packaging fundamentals of high performance applications. As also William previously present, for the silicon node, the cost trend actually is keep increasing with silicon nodes progress in IC scaling is becoming more expensive, and also the associated yield can be problematic and be further affecting effective cost. From the slide, you can see from the left, the wafer product cost entirely covering manufacturing cost, engineering cost, and new product introduction cost. So the wafer cost is keep increasing with the silicon scaling. And also the engineering design, because the mask layers cost increase is also increased. And also the new product introduction cost is increased for every technology node, because all these associated costs for the mask design cycle, all this and learning curve, including the yield landmark costs. And also here the right side from the MD HIR, you also summarize the entire effective cost after silicon node 14 and 16. The entire cost, the landmark rate is obviously increased. This page is summarized from the John Sharp HIR. Also, the performance trend is not matched. Actually, the silicon node progress does not seem to provide proportional performance and power benefits anymore. From here, especially the cross frequency, you can see from a long time, about 5 years ago is about 10 years ago is almost already saturated, and the power also saturated soon, and the thread performance also is flatly. So overall, this silicon node did not provide enough effective performance. Then here we can see the for different silicon technology in terms of product of CMOS logic, memory, and analog. From scale point of view, the CMOS logic is the best one. It can scale fast, and memory somehow is a bit late. And the analog actually is really not so catch up, and you will not be able to catch up actually due to its performance request and design request. And from technology, no case, CMOS logic is the leading one, and memory is the second one, and analog is the third one. So interconnect layer case, CMOS logic has the most layer, backend layer, and memory has less, and analog somehow petit. So from product development point of view, we have typically different approach. One is a transistor focus, is basically try to make transistor density as high as possible. So you basically consider more on transistor scaling, and then better performance per cost. So and another view from the strategic point is to focus on system level, which focus more on increased functionality and lower cost. And technology case is more focused on technology, device and circuit innovation and system integration from the big picture level. For the system focus could actually can be carried out on either this chip level or package level. The chip level case is SoC, which means system on chip, and system package level is SiP, system in package. For example, the SoIC, but the latest progress is TSMC's SoIC is a kind of 3D SoC. So from system innovation and heterogeneous integration point of view, with the scaling of the silicon node, still there's two ways to go. One is the SoC chip integration, another is SiP. So, and for the SoC and the SiP actually is always competing. So you competed from the manufacturing point, mainly is silicon node, and the IP and IP use, and basically for the design and engineering cost, consider point of view, and for development cycle time, new product introduction costs, and also the hardware and software entire integration and performance trade-off and product market share strategy. You want to count out the product is version 1, 2, 3, somehow like that, and also, or you want to consider like from profit version like 12 directly. Another key point of view for our industry is actually is the supply chain variety and also the safety. You typically the fabless company don't want to at least has two sources of this supply to secure the delivery of the product to end customers. For example, current chip shortage for the entire industry, especially automotive, or people even thinking about maybe the entire advanced chip from TSMC will become a problem. From this progress of silicon law and the cost point of view, the industry actually start to respond from previous roadmap from ITRS convert to this HIR. And the key focus actually is HIRS is focused more on CMOS, Moore's law driving, and because the almost end of the Moore's law, the HIR is focused more on system and application driving. So for the actually heterogeneous integration point of view, high-end application mostly focus on is the FCPJ packaging. For FCPJ packaging, the left side is this four kinds of basic structure. If is only one SoC chip point of view, this is either with stiffener ring or the stiffener ring pass the spreader two piece of structure, or this forged dies lead for the better warpage control and also heat sink control. And then also this is a hell ties lead for different kinds warpage control. So with the 3D progress with multiple chips, so becomes find out, for example, the CoWoS 2.5D with silicon interposer. So basically, this SoC chip becomes a two-chip chiplet or SoC plus HBM -2 or -2E. So then for larger FCPGA types chiplet involved currently most advanced one is the first one is the CoWoS from TSMC, or different company have a different name. Basically is this interposer uses silicon TSV interposer, and the second one is the representative is the Intel's one EMIB. Then the third one is this the fan out on substrate, or RDL first the die last one, or die first RDL last one, or this also the die last one also covers this fan out RDL as an interposer, and the third one is 2.1D. Basically, in our JCET group, we call it UFOI of our XDFOI family. Basically, this is a fine RDL layer is embedded inside the BGA substrate. Or some other companies, 2.5D is building the fine RDL layer entirely on the RDL on the FCPGA substrate like Hitachi promoter. Then there's a sixth one is RDL on rigid substrate. Basically, this is something like Cinco proposed. Basically, this organic substrate interposer with stick substrate. Then the die is a feature on it. Then also then attach on the typical FCPGA substrate. So basically, this the organic interposer also have the feature of 2-micron line space. So for 2.5D interposer case, previously the first generation actually is purely passive RDL interposer, but now because of this heterogeneous integration progress, started going to this active interposer. Basically, active interposer has both TSV as a basic feature, then also has this change capacitor as a decoupling capacitor to improve the performance and like the voltage drop. Then is derived directly under the SoC or the other chiplets. So basically, the process flow is active interposer, just like the CoWoS approach. Basically, from the TSV and backend offline, then the optional PIRDL on top of the with the optional inductor like IPD. And also the 2.5D assembly with die-to-wafer address when you can optional put in address the bar for stiffer control and voltage control or for molding. Then also the TSV backend exposed with the backend RDL and also the C4 bumping. Then this fan out or the 2.5D die package is friction mount on the substrate. Then finally attached with the downside capacitor or IPD, then placed with the solder board. So basically for our thinking as an OSAT, we basically consider the model is a foundry prepare the TSV wafers and like our JCET does the rest. So here is another type of chiplet application is CSP type fan out or the chiplet application. Is first is die first like info ME series from a DCA or AC, then EW from our stat chiplet JCET and AC and Nani and Anchor. Then also the RDL last RDL on the carrier. This several other old company are doing mainly is for high end or especially for chili because the cost consideration and no good die loss consideration. Somehow the RDL last on carrier is more preferred. And another is fan out on the substrate. This is basically is die first fan out for the smaller, relatively smaller packaging because the yield consideration still valuable. Then the die last RDL on the carrier, this is also is for if we have multiple chiplet, consider no good die loss, we also prefer the RDL last on the carrier. Then another mention is this RDL hybrid substrate basically embed a fine RDL inside the substrate. It can be used in the CSP package as well. And this can, for example, use in the cordless substrate build up. This will provide higher performance because of the shorter connection. Here is another trade we can see from on the industry. Recently, this reverse engineering showed this Apple's M1 CPU application in the iPad or Mac. So basically, this is SoC die, and here is the memory. So then they use the half lead to control the thermal management and also the voltage. This is the structure from system class. You can see the difference from conventional this CPU. Then for challenge case, as this 5G and automotive progress, automotive also start to use this 2.5D and also SiP. But currently 2.5D and SiP's reliability performance still could not really meet the automotive industry requirement in terms of grade 1 and grade 0. For this one there's a long way to go. This is and we have to solve this reliability requirement, especially for the ADAs and also the automotive drive. Then in our JCET viewpoint view of the chillers will be preferable to chip first the fan out for chiplet, mainly because the no good die loss. Manufacturing cycle time for high density chip first, the fan out is a showstopper because we have to go sequential process flow. And why for the truly RDL first case, we can proceed in parallel. So process yield concerned on the multi-layer ultra high density RDL for the chip first, the OSAT is unable to hide the cost yield and in the no good die pricing. So that's another reason we have to use somehow prefer the RDL first, chip last for Chile in our OSAT point of view. Then chip middle approach in fan-in POP may be another variable 3D option, and FC assembly on multi-layer ultra high density RDL with low dense backend RDL on the mode wafer. Somehow we call it is a fan-out interposer. Optimized approach for the yield and cycle time and thickness would be permissible for this POP approach and also for other FC CSP's approach. And silicon interposer with TSV still will be required for high-end application with wide bus architecture like AIB of Intel promoter, and requiring sub-micron routing density. And for TS release, RDL interposer preferred as alternative to silicon interposer, mainly because of the mid high-end routing density 2 micron feature and R2 for high density routing layer, mainly because the yield loss even with high density routing layer. So that's why we prefer limited effort high density routing layer. And silicon bridge will be difficult to implement for our OSAT in practice for more than a few die per package. Then JCET readiness for this application, we already developing this XD fan out 2.5D on the substrate. Basically, is RDL first with 2 tree or 3 tree or 4 tree. Then after the fan out 2.5D, we put the fan out package on top of the substrate with 14 to 20 layer of substrate. And then also the chip middle 3D POP, this application we have previously developed a year ago, but now we restarting this practice with chip middle 3D POP. This POP can be used for typical POP APU package, can also be used as an interposer, bridge interposer for high-end 2.5D chiplet packaging. Then also we are working with substrate supplier together for this XD fan out 2.5D hybrid substrate. Basically, we will build the RDL layer with less than 4 micron line space, and we deliver this RDL layer to the substrate supplier. Substrate supplier will build the additional layer on top of it, and before this collies or for the FCBGA application. Then the silicon interposer assembly case, basically we still mainly collaborate with foundry in advanced 5-pitch bonding. So this involves either the interposer on substrate first or die to wafer first, and then on substrate. Here it shows some our XD fan out 2.5D TS release process flow. Basically, for example, what we're working on is 65 by 65 package size. That size is currently is 13 by 26, and silicon is like 7 nanometer, and with bond pitch of 330 micron with 14 layer of FCBJ substrate. BJ pitch is about 5 mm. So this package will be already codified. So basically, it's a conventional this glass carrier with release layer. We build R3 layer of RDL, and after that we attach chip, free chip on the micropad, and after that we apply the molding. Then we do the debond and do the backwinding. Backwinding can be done either or also after the C4 bumping. Here we show is the first. Then we after debonding we play the bond and singulate. Then this singulated package is attached to FCBGA substrate applied with the underfield. Then Then after that, attach with the thermal lead, then also attach the, this solder board and also lens side IPD capacitor, for example. So for this current XD fan out circulation case, currently we are prototyping mainly is for metal layer. So then minimum VR size is 15 and minimum line space is 4x4 and maximum size 14x14. R&D case we are doing currently is 4 micron still. Minimum VR size mostly is 15, but we are working on the 8 micron size as well. And line space, we are working with 2 micron line space. The mask size is 14x14, mainly constrained by the stepper. So basically, what we showing, we are using the electric material is photosensitive polyimide material. RDL is made by the selective electroplating. The recommends is there's no V1 opening for 2.1D application. So basically here shows the material some property basically at the different frequencies. So dissipation factor Q value is quite consistent across the frequency. That's the reason we choose the PI sensitive, photosensitive PI. And another application we are basic technology for interconnection. We use actually is the laser assisted bonding, which will be important for this, for example, cordless substrate or other substrate with higher warpage. And with the fan-out package or the 3D package size becomes bigger, the total warpage also becomes bigger. So to minimize the warpage mismatch, we developed this. We also working on this laser assisted bonding process to reduce the cost. And also another consideration is for laser assisted bonding contribute less the stress on the ultra-low-K backend of the material. That's what the reason we working on this laser assisted bonding. And this laser assisted bonding basically use this laser IR laser to heat up this silicon die, and which can be programmable with the different size, and then heat up the silicon to certain degrees of temperature, and also the PCB temperature is controlled like 70 to 80 degree. Then after reflow, you can be similar. You take a bond together with the micro pad. Then the warpage and also performance can be the yield can be much better control than typical MR or the TCB bonding. So here is our FCBGA roadmap. We can perform a single SOC FCBGA without lead, and also multiple die, and also we can manufacture this multi-package FCBGA, including the top side and the left side. We also have for different kinds of even other components together for the automotive application. Then also multi-chip this FCBGA package. So for the lead type, we have a flat lead and also a ring type with this multi exposed with field assist molding. Then also this SOC pass package type. We are working on this 2.5D TS release FCBGA with 2 die or 3 die or also 5 die. Then we are also working on different number of packages together with OC with this 4 die lead. Then other types multi-packaging module FCBGA with HC. Then other market reference here shows you can see industry, for example, Samsung, they are working on the 3D FCBGA HD fan out multi-core module as well. So and also together with multi-die. Then from the Prismark, they can industry research report, it shows like AMD on chip network design to determine whether data center have lift chip to prevent the deadlock of with on the active interposer. So that part is also working on this. The Intel's Lakefield hybrid CPU use high bandwidth with this EMIB. Then the LITID working on this active interposer. They do a very good explanation of this the active interposer's advantage and how to do it. Then also they go working on the interposer with integrated passives, controlling the supporting power management and also this chip interconnection. The integrated passive, if we're talking about chip capacitor in the interposer, is major advantage is can provide higher reliability over the 150 degree for automotive application. So here is typically the year research report mentioned what these different application for the 2.5D, 3Ds, SIP application, including mainly is CPU, GPU, the FPGA, memory, and sensor, and also optical electronic performance. For example, photonic network application, typically people consider use silicon interposer with photonic circuit on top of it as an interposer together with IC drive or porting type.